This discussion pertains to transformer upgrades and adherence to the National Electrical Code, specifically concerning a scenario involving a 12,500 to 480 volts transformer. The initial setup includes a 2500 kV ampere transformer with plans to increase its capacity to 2880 kV amperes. A separate 1000 kV ampere transformer is connected using number 2 American wire gauge conductors. The intent is to increase the fuse size to 180 amps. Let's consider several relevant articles from the NEC. NEC 240.92 addresses secondary overcurrent protection for continuous loads exceeding 100 feet. It mandates that the overcurrent protection must be based on both the full load current and the conductor ampacity. NEC 450.3 concerns overcurrent protection of transformers, stating it must be based on the transformer rating and the secondary conductor ampacity. NEC 210.19, 210.20, 215.2, and 215.3 outline how conductor ampacity is determined by factors like temperature rating, insulation type, and installation conditions. NEC 220.200 covers branch circuit overcurrent protection, specifying that it must be selected based on the circuit ampacity and the motor load. NEC 230.200 deals with service overcurrent protection, requiring selection based on the load rating of the service equipment. Several issues need to be addressed. Firstly, secondary conductor ampacity. Because the secondary conductors from the 1000 kV ampere transformer exceed 100 feet, NEC 240.92 dictates that the overcurrent protection must be based on the full load current and conductor ampacity. Secondly, fuse ampacity. The proposed 180 amps fuses may exceed the allowable ampacity for the secondary conductors. NEC 450.3 suggests that the maximum fuse size for a 1000 kV ampere transformer with number 2 American wire gauge conductors may be lower than 180 amps. Thirdly, future load increase. A planned load increase could potentially overload the existing transformers. Fourthly, the loss of continuous load protection. Fusing the secondary conductors at a high ampacity could compromise continuous load protection for motors, potentially leading to overheating. Here are some recommendations. Firstly, upgrade the secondary conductors. Upsize the secondary conductors from the 1000 kV ampere transformer to meet the full load current and ampacity requirements outlined in NEC 240.92. Secondly, reduce fuse ampacity. Install fuses with an ampacity that aligns with the conductor's capacity. Thirdly, consider a transformer upgrade. Evaluate the possibility of upgrading the existing transformers or installing an additional transformer to accommodate the future load increase. Fourthly, follow proper installation practices by adhering to NEC requirements for transformer and feeder installation and maintenance. Let's dive deeper into the NEC articles mentioned. Focusing on NEC 240.92, the critical aspect here is the length of the secondary conductors. If the conductors exceed 100 feet, the overcurrent protection requirements become more stringent. The ampacity of the conductors must be a primary consideration when selecting the overcurrent protection device, such as a fuse or circuit breaker. This is because longer conductors are more susceptible to voltage drop and can experience increased impedance, which can affect the performance of the connected equipment. The NEC aims to ensure that the conductors are adequately protected against overcurrents that could lead to overheating and potential fire hazards. NEC 450.3 provides specific guidelines for overcurrent protection of transformers. This section requires that the overcurrent protection be based on the transformer's rating and the secondary conductor's ampacity. The intent is to protect the transformer from overload and fault conditions, while also ensuring that the conductors connected to the transformer are adequately protected. The transformer's nameplate should provide the necessary information to determine the appropriate overcurrent protection size. This includes the transformer's kilovolt ampere rating, voltage, and impedance. The secondary conductor ampacity must also be considered, as the overcurrent protection device should not exceed the conductor's ampacity. NEC 210.19, 210.20, 215.2, and 215.3 address conductor ampacity requirements. These sections outline the factors that influence a conductor's ampacity, such as its temperature rating, insulation type, and installation conditions. The temperature rating of a conductor is the maximum temperature that the conductor can withstand without degrading its insulation. The insulation type also affects the conductor's ampacity, as different insulation materials have different temperature ratings. The installation conditions, such as whether the conductor is installed in free air or in a raceway, can also affect its ampacity. The NEC provides tables that list the ampacities of different conductors based on these factors. NEC 220.200 provides guidance on branch circuit overcurrent protection for motor loads. The overcurrent protection device should be selected based on the circuit ampacity and the motor's full load current. The NEC provides tables that list the full load currents for different motors based on their horsepower and voltage. The overcurrent protection device should be sized to protect the motor from overload and fault conditions while also allowing it to start and run normally. NEC 230.200 addresses service overcurrent protection, which protects the entire electrical service from overload and fault conditions. The overcurrent protection device should be selected based on the load rating of the service equipment, which includes the main service disconnect, the service conductors, and any other equipment connected to the service. The NEC provides guidelines for calculating the load rating of the service equipment based on the connected loads. Returning to the specific scenario, the existing number 2 American wire gauge conductors may not be adequate to handle the increased load of the 1000 kV transformer, especially considering the length of the run exceeds 100 feet. The proposed 180 amps fuses may exceed the conductor's ampacity, potentially leading to overheating and damage. The planned load increase of 1800 kVA and the 2500 kVA transformer will push it to its limits. It is crucial to perform load calculations to determine the actual load on the transformer and ensure that it is not overloaded. Overloading a transformer can reduce its lifespan and increase the risk of failure. The loss of continuous load protection for the motors is a significant concern. Continuous loads, such as motors, require adequate overcurrent protection to prevent overheating and premature failure. Fusing the secondary conductors to high ampacity may not provide sufficient protection for these loads. To address these issues, upgrading the secondary conductors from the 1000 kVA transformer is recommended. This will ensure that the conductors can handle the full load current and meet the ampacity requirements of NEC 240.92. Reducing the fuse ampacity to match the conductor's ampacity is also essential. This will provide adequate overcurrent protection for the conductors and the connected equipment. Consider upgrading the 2500 kVA transformer or installing an additional transformer to accommodate the future load increase. This will prevent overloading the existing transformer and ensure a reliable power supply. Ensure that all electrical work is performed by qualified electricians and in accordance with the NEC and other applicable codes and standards. Safety should always be the top priority. It's also crucial to understand the difference between conductor ampacity and overcurrent protection. Conductor ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. Overcurrent protection, on the other hand, is the use of devices like fuses or circuit breakers to protect conductors and equipment from excessive current flow due to overloads or short circuits. The overcurrent protection device should be sized to protect the conductor, but it should not exceed the conductor's ampacity. It's important to note that the NEC is a minimum standard and that, in some cases, it may be necessary to exceed the NEC requirements to ensure a safe and reliable electrical system. For example, in critical applications, it may be prudent to use larger conductors or more robust overcurrent protection devices than what is required by the NEC. Regular maintenance and inspection of electrical equipment are also essential for ensuring its continued safe and reliable operation. This includes checking for loose connections, damaged insulation, and other signs of wear and tear. Any problems should be addressed promptly to prevent potential hazards. Finally, it's always a good idea to consult with a qualified electrical engineer or electrician when making changes to an electrical system. They can provide valuable insights and guidance to ensure that the work is done safely and in accordance with all applicable codes and standards. In summary, when dealing with transformer upgrades and electrical system modifications, it's crucial to consider the NEC requirements, conductor ampacity, overcurrent protection, and the potential impact on the overall system. By following these guidelines and consulting with qualified professionals, you can ensure a safe and reliable electrical system. The information provided is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or electrician before making any changes to an electrical system. Remember to prioritize safety and adhere to all applicable codes and standards. Always energize electrical equipment before working on it and use appropriate personal protective equipment. The goal is to ensure a safe and reliable electrical system that meets the needs of the facility while also protecting people and property from electrical hazards. This requires a thorough understanding of the NEC, careful planning, and attention to detail. By following these principles, it is possible to create an electrical system that is both efficient and safe.